And welcome to today's video. In this video, I'm going to be explaining to you how to complete bond enthalpy calculations. These are particularly relevant for NCEA Level 2 for the Structure and Bonding Standard AS 91164. They may also turn up at Level 3, but not normally. Okay, so the idea behind these bond enthalpy calculations is that when reactions happen, bonds break and new bonds form. Okay, so this is obvious. Breaking the bonds between certain atoms will require energy. So that's an endothermic process. When we form bonds, the process of forming bonds is an exothermic process, and that releases energy. Each particular type of bond has a different amount of energy associated with it, and that's what we call the bond enthalpy. So by summing up the enthalpy required to break all the bonds that are breaking in the reaction and the enthalpy required to make all the bonds, the enthalpy released when we make all the new bonds, then we can work out the overall enthalpy change for the reaction. Okay, so let's be really clear. Breaking bonds takes energy, making bonds releases energy. So we use a very simple calculation which looks like this. Now that looks fairly ugly, but what it's just saying is that the enthalpy change for the reaction is equal to the sums of the enthalpies of the bonds that are broken minus the sum of the enthalpies of the bonds that are being formed. Now, what does that really look like in practice? Because this is an interesting concept, but what does it really look like in practice? Well, in reality, you will have an equation and you will be given bond enthalpy values for that equation. So these come from standard data tables usually. You're not expected to memorize these. Okay? You just have to know how to apply these. Now sometimes you will be given some bond enthalpies and asked to calculate the enthalpy change for the reaction, which is what this example works through. Sometimes you'll be given the enthalpy change for the reaction and asked to work out one of the enthalpies of the bonds. And I'll show you an example of that shortly. Okay, so in this sort of example where you've been given an equation and you've got a bunch of bond enthalpies, the first thing you have to figure out is what bonds are actually being broken and what bonds are actually being formed. And for that, I really recommend you draw out the structure. Sometimes in NCEA they will give you the structures of the substances, but if they don't, please do draw them. Otherwise, people make mistakes because they miscount things. Okay, so we've got methane, one methane, two O2s, a CO2, and two waters. And I draw them all out because then I can actually count up the bonds properly. So if I look at it, all of the bonds in the reactants are going to have to break, and all of the bonds in the products are going to have to form. So what have I got? In the reactants, I have 1, 2, 3, 4 bonds between carbon and hydrogen and 2 carbon-oxygen double bonds. Now please be aware that a double bond is not the same thing as 2 single bonds. They have quite different bond enthalpies. So if it's a double bond, you look at the enthalpy for the double bond. Don't think about doubling the enthalpy for a single bond. Okay, so breaking, I've got 4 carbon-hydrogen bonds, 2 oxygen-oxygen double bonds. Forming, I have 2 carbon-oxygen double bonds and 1, 2, 3, 4 oxygen-hydrogen bonds. So let's work through this calculation. My bond's broken. I've got 4 carbon-hydrogen and 2 oxygen-oxygen double bonds. And I can just multiply those numbers directly. I quite like working it out bit by bit, because then I'm less likely to stick it in my calculator in a dumbass way and stuff it up. If you are really confident with your calculator skills, then feel free to try and stick it all in one big thing, but I don't like doing that personally. So those are the bonds that are breaking. The bonds that are forming, we've got 2 carbon-oxygen double bonds, 4 oxygen-hydrogen bonds, so we can multiply those up. And you get your formula, put the numbers into it. Now you'll notice that I've got brackets. And the brackets are quite important, especially in the second bit. Because if you don't have brackets in here, if you just type 1652 plus 988 minus 1598 plus 1836, if you type that into your calculator, you'll get the wrong answer. You need the brackets because it's implying that you've got to add these two together and add the second two together, and then you can subtract it. That's what you're telling your calculator. If you do that, you should find out that the enthalpy change for the reaction is minus 794 kilojoules per mole. And that makes sense that it's an exothermic reaction. Delta H is negative because it is a combustion reaction. You're burning methane, and you would expect combustion to give out heat. Okay, something slightly trickier. This was the 2019 NCEA exam question. And this is talking about the reaction between propane and oxygen. So it's a different combustion reaction. We like combustion reactions, they're nice and easy to do. But with propane, it's a slightly more complex molecule. So we've got one propane reacting with 5 oxygens to make 4 waters and 3 CO2s. You can see there that you're given the structures of propane, oxygen, water and carbon dioxide, and some bond enthalpies. You're not, in this case, being asked to calculate delta H because you've actually been given that. You're being asked to calculate the bond enthalpy of the carbon-oxygen double bond. So this is simply an algebra problem. But the first thing you have to do is calculate how many bonds are being broken and how many bonds are being formed. You've been shown one of each of those molecules, but remember, if you look at that balanced equation, you've got 5 oxygens and 4 waters and 3 carbon dioxides. So total bonds being broken, you've got 2 carbon-carbon bonds and 8 carbon-hydrogen bonds. You've got an oxygen-oxygen double bond for each mole of oxygen, or each molecule, but there are 5 of them, so you're going to have 5 oxygen-oxygen double bonds. Bonds being formed, we've got 4 waters. Each water has 2 oxygen-hydrogen bonds, so there's going to be 8 of those in total. And 3 carbon dioxides. Each carbon dioxide has 2 double bonds, so that's 6 in total. So start with the formula. Figure it out and substitute some things into there. So I've put the enthalpy in there and I've written down all the bonds. Then you can substitute your numbers in and calculate them. And I'm not going to do that bit by bit because I'm sure you've got a calculator of your own. But do be careful. And like I say, I really recommend doing it bit by bit. Now the next step is I'm going to take the last term, 3704 plus 6 carbon-oxygen double bonds, and I'm going to add that entire term onto the other side. Just to rearrange it, that then gets my carbon-oxygen bonds over there. Then what I'm going to do is I'm going to remove, and you'll notice I've also summed up that other term as well. I'm then going to remove the 2 numbers, so I'm just leaving the carbon-oxygen bonds on one side, so I'm just going to shift those across and work through solving this. Divide the whole thing by 6, and the average enthalpy of the carbon-oxygen double bond is 805 kilojoules per mole, rounded to 3 significant figures with units. Okay, I cannot stress that enough. You must round accurately to 3 significant figures and you must use units. So this was an excellence question in last year's exam, in the 2019 exam. There was an achieved point for basically attempting to substitute into the equation appropriately, a merit point for doing it mostly right but making one minor error, and an excellence point if you got the whole thing right. I hope this helps you figure out how to solve bond enthalpy calculation questions, and I will see you in my last video soon, which is going to look at thermochemical calculations. See you there.